Hello everyone, my name is Sohail Rehan Malik of 2nd CSC from Srinivas Ramanujan Institute of Technology. So the topic today I'm going to discuss about is on Eulerian graph and Hamiltonian graphs with examples from the subject discrete mathematics and graph theory. So without any delay, let's get into the topic. Coming introduction to the graph theory. Here, graph theory is a branch of mathematics that studies the properties of graphs. A graph consists of vertex. Let me show you the vertex consists of a vertex or called as nodes connected by edges. These are called edges. Understanding these specific type of graphs like Eulerian and Hamiltonian graphs is crucial various applications. Firstly, what is an Eulerian graph? An Eulerian graph is a graph in which there exists a closed trail that visits every edge at least once, exactly once. A necessary and sufficient condition for a graph to be Eulerian is that all vertices have even degrees. Even degrees, that is, it may be two connections, or it may be four, or it may be six, or any more. But it should be in even. Eulerian graphs are named after mathematician uh, Leonhard Euler, who studied these concepts in the 18th century. Let me show you here the graph Eulerian paths from examples 1, 2, 0, 3, 4. Vertices. Example of Eulerian graph. Let me show you an example. Consider a simple triangle with vertices A, B, and C, where each vertex is connected to every other vertex. In this graph, each vertex has a degree of 2, that is, two connections, which is even, as 2 is even. So therefore, this triangle graph is an Eulerian graph because one can traverse every edge exactly once and return to starting vertex. Let me show you here in the image maximum number of edges that n vertex graph can have. Here n is equals to 4, that is valid graphs. Here edges 0, edges 1, 1, 2. Here it has 2 degree. So, but here one vertex is not connected yet, so we can't coming to end that it is an Eulerian graph. So again coming to the edge 3, no here, but the last the node is not returning, so it is not connected, so I can't tell it is an Eulerian graph. Coming to the edge 4, so every vertex has 2 degree of 2, so I can say that it is an Eulerian graph. Coming to these edge 5 and edge 6, here it cannot be an Eulerian graph, as here the vertex consists of 3 degree of 3, and here this vertex as well consists of 3, so these can't be said as a Eulerian graph. Here also it consists of 3 vertex 3, so it can't be as a Eulerian graph. Characteristics of Eulerian graph. All vertex in a Eulerian graph must have even degrees except for potentially two vertices in a semi-Eulerian graph. A connected graph with all vertices of even degree has an Eulerian circuit. We can also call it as a Eulerian circuit. If exactly two vertices have odd degrees, the graph has an Eulerian path but no circuit. There is no circuit. Here are some examples of it. Now coming to the Hamiltonian graph. Coming to the Hamiltonian graph is a graph that contains a Hamiltonian cycle, which is a cycle that visits every vertex exactly once before returning to the starting vertex. Here, the point to be noted that here, before returning to the starting vertex, so it should be returned to the starting vertex. So, but before that, it should be exactly meted once. Unlike Eulerian graphs, the focus is on the vertex rather than the edges. Here, before in the Eulerian graph, you can see that there are edges. Edges are the matters that all the edges should be connected to each other. But in this case, in this Hamiltonian graph, it is not mentioned that it should be connected only. So the existence of a Hamiltonian cycle is generally harder to determine than that of an Eulerian path or circuit. So this is a graph and this is a Hamiltonian graph. So without these connections also, I can say it has a Hamiltonian graph, but it can be a graph here, as you can see. Normal graph should be connected to each other. Vertex should be connected to each other. Example of a Hamiltonian graph, you can see here all the possible readings in the image. Here the starting image starts from degree 1. Let me say as degree 1. Degree 1 to degree 2. Degree 2 to degree 4, degree 4 to degree 5, degree 5 to degree 3, and degree 3 to degree 1. So here it meets all the vertex, but the some of the edges are left. But as I have said before, it only focuses on the vertex rather than edges. So it can be considered as a Hamiltonian graph. So Hamiltonian graph is the major thing where all the vertices should be meet at a point. Hamiltonian circuit. There are no simple, necessary, and sufficient conditions for a graph to be Hamiltonian, making it a complex study. Hamiltonian graph may have vertex of varying degrees. Unlike here, the point to be noted, the Hamiltonian graph may have vertices of varying degrees, not an even degree or not an odd degree. It may be any degree. It may be even, or it may be even, or it may be odd. Many algorithms exist for checking Hamiltonicity, but they can be computationally intensive also. Here, as you can see, exactly once without repeating the edges or the returning the starting vertex. So it can also be written, but sorry, it should not be written or repeat. Comparison between Eulerian and Hamiltonian graphs. This is a perfect example to show you. Hamiltonian Eulerian is the one which have even degrees, I have said, and also should connect all the uh, edges. Here you can see the degree 2 and satisfy Eulerian, and also Hamiltonian as well. Hamiltonian is the thing which I have said it should meet all the vertex starting with this, coming to this and this and this and last for this. So it also can be said as Hamiltonian graph. Coming to this point, it is not a it is can be said as Eulerian graph as it is connected to all vertices with an edges. So, but it cannot be Hamiltonian as if I start here. So coming to this point, and this point, I can't return as here. There would be an error, so it can be not Hamiltonian graph. Coming to this, it is not Eulerian graph as it has 3 degrees. That is odd degree, so it cannot be an Eulerian graph. But it can be Hamiltonian graph. That is, if I start from this, I can say it can be goes to there and from this third point and coming to this fourth point and last returning to this point. So it can also be said as Hamiltonian but not Eulerian graph. These are the example, and this in case also this it can be repeated as, but it is not Eulerian as I have said. This edge is missing in Hamiltonian starting edge. If I say this as a starting edge, this returns a value. Both types of graphs play significant roles in solving problems in network design and optimization. Applications of Eulerian and Hamilton. These are the some applications. Understanding these graphs has implications. So computer science, logistics, and algorithms we generally use in this. Coming to the conclusion, in summary, Eulerian and Hamiltonian graphs are fundamental concepts in graph theory with distinct definitions and properties. Both types of graphs have their own significance in practical applications and theoretical studies. By exploring these graphs, one can gain insights into complex systems and optimize various processes. You can also see some about cycles and paths and examples. Yeah. And I hope you all are clear with the Eulerian and Hamiltonian graphs. So that's it from the topic. Thank you. Have a nice